right, hello everybody, and welcome back to an Exolife Planet Hangout. Exolife Hangout, sorry. We haven't had these in a real long time, mostly because we've not really had a lot of updates to go through with a lot of the subject. But today we're going to revisit some old friends of ours from the Planets Foundation. Jeff Kuhn et al. Is here to talk to us about the mini elf, which I don't really even know what that is. So I'm going to learn about that as well. And before I bring everybody up, though, I just want to let you know that I am streaming, as I always am, on YouTube, but I'm also streaming on my Facebook channel, on my Facebook page, also on Twitter, as well as Twitch, on the Twitch Deep Astronomy channel. So this is normally the time I do T Cubed, which is Tony's Twitch Tuesday, but today we're doing this hangout instead. And I am looking at all of the comments. Neil, I see you. Crazy Cat Christiana is here. Galaxia, all you guys are here. So please leave comments, and I'll be seeing all of them, and I'll put them up like this, so you'll be able to see them on the screen. So that'll be one. That's one new feature I've got going for me. So before I bring up my guests, I just want to say a little bit about the Planets Foundation. They're involved in building ground-based telescopes that are designed not just to, well, they're designed to search for life elsewhere specifically, but they're also designed, these are all ground-based telescopes, by the way, which is quite remarkable. They're designed to actually image exoplanets as well and look for biosignatures. These are specially designed telescopes, which we'll talk about here in just a bit, that will help us find life in the universe. They're trying to get the funding now to get these built, and we're going to get an update during this hangout on the state of the project. But they're, in addition to doing that, they're also involved in space, or in STEM outreach, and they've got a Kickstarter that I want to point your attention to. The link to that is in the description box below, so please check it out. And they are in the process now of building a they've got a children's book out in the Kickstarter's campaign that's called Lana and Tardi Space Adventures, and it looks really neat, and I'm going to get one for my granddaughter. Yes, I have a granddaughter. Don't say nothing, okay? Yes, I have a granddaughter, and she's going to be getting a copy of this book as well. I'm very excited about it, and I'll just give you a little quick update, or a quick view of what it looks like. Let's see if I can bring this up, and it's a background, so I have to do this. Let's see. Where'd it go? Oh, it's still learning my new system here. Well, anyway, here is a... You can't hear me while I do that, but that is that's one of my... It's a really neat looking thing, so please go check it out. The link is in the description box. Okay, so let me bring up my guests here. First, bring up... all of these guys are from either from the Planets Foundation or part of the consortium. First up, I'll bring up Jeff Kuhn, who you guys realize. Hi, Jeff, are you there?
Hi there.
Also with me is Ye Zhou, also from the Planets Foundation, and Gil Moretto. He's here as well. Hi,
Hello.
Gil. And finally, I'll bring up Rafael Robolo. He is the director of the Institute at the Canary Islands, who is also a member of the consortium. Welcome, everybody. Thank you for taking time out to join us. And Jeff, let's start with you as always. Let's get an intro into what you guys are working on. And you know, it's funny, when I was setting this up with Kevin, we were talking. He kept talking about mini elf, and I'm like, "What is a mini elf? I have no idea what that is." So talk about elf, but also what the heck a mini elf is, because I don't know what that is either.
So Tony, the last time that we talked, we were in meetings to discuss this idea of an Exolife Finder Telescope. So everybody in this meeting, I think, shared the opinion that the world deserves a telescope which is devoted to looking for evidence of life in the universe and studying in great detail the exoplanets that we now know are around most stars out there. So in your meeting, you have some real experts. Rafa is the director of the Institute Astrophysica de Canarias, and he is an expert in the detection of small stars and exoplanets. And he's joined the consortium as hopefully a host for the Mini ELF telescope, which is there's a whole bunch of technology that hasn't really been tested, and so that test of these new technologies is this telescope that we call the Mini-ELF. It's, rather than being 30 meters across, it's only about 4 meters across. And that's the telescope that we're now building. Ye Zhou is the guy that knows how to build telescopes. He's deeply involved in his company. That he was one of the principals for, over the years, built big pieces of the Keck, and they're responsible for the 30-meter telescope. They are joining us and basically taking on the task of taking the concept with this new technology into something that we hope really works and we can demonstrate with the small telescope. And Gil is from Lyon, at the Observatoire de Lyon. He is deeply involved in all aspects of this, and has been part of the Planets Foundation and the push to create a telescope that can look for life for a long time. So we're enthusiastic. We're bound by this common vision that someday we're all going to wake up to the news report that says that there's life on a nearby exoplanet, and we hope to be some of the ones that are providing the instruments that will actually do and solve that problem.
Okay, so yeah, so I've got a picture of, I've got some of your slides up here, just a picture of this. Now, I should also point out that the ELF stands for Exolife Finder, and you can get a lot of information from what they're doing from the Planets Foundation website, which is, I believe, exolife.org. Is that right? Is that your URL?
It's planets.life.
Oh, okay. So Planets at Life, you said?
Planets.life is
oh, planets.life. I thought it was I thought Exolife was in it. So planets.life is a place where you can go to get more of their information on that. So yeah, let's talk a little bit about what your role is on the, tell us what you're doing on the Exolife telescope.
Okay, well, I'm an engineer, and so what we do is to design a very large mechanical system, very often precision systems, as Jeff already mentioned, and for the past probably 1 or 2 decades. And I used to be with a company called Dynamic Structures. We did a lot of large enclosures, like for example, Keck and Gemini and a few others, and also some telescopes. And so in the past few years, we've been working on the 30-meter telescope. And so my role here is engineer. And as we know, the ELF, that will be eventually, if it's being built, it will be a huge telescope and involve quite some I was in revolutionary technologies and in building telescopes. And as we know, a lot of large telescopes, like ELT and EMT.
Oh, somebody's got
a lot of echoes. Yeah. Okay.
Yeah, that was Raphael.
All right.
I had to mute you, Raphael. Sorry.
Okay. Sorry. All right. So my role here is to design telescope and try to, as Jeff already touched a little bit, and because ELF involve a lot of new technologies, not only in the in optics, but also in the mechanical part of the telescope. And what we hope to do is through Mini-ELF, we can verify a lot of new techniques, and that's involved with ELF, and so that ELF can serve as a pathfinder and give us a platform so that we can verify a lot of new techniques and a lot of new technologies that we can transfer to the big ELF, and also to reduce the risk of dealing with a large new big project.
Okay, I'm trying to get a picture of the other ELF that we had. Now I had everything queued up, but then Jeff gave me some last-minute slides. Jeff, in the slides you gave me, is there a picture not of Mini-ELF but of the ELF system, or is it all Mini-ELF? Because I want to show that first. Let me just see if I can do this real quick.
I'll queue one up on my screen, and in a minute you can share it if you want.
Okay, yeah, go ahead, because I want to show people what the Exolife Finder Telescope looks like because as I understood it, so you guys had several layers of telescopes that you were going to, hang on, just let me get that you were going to use for um, finding life elsewhere. You had the ELF, which was the Exolife Finder, which has this ring of primary mirrors around a circle that were each off axis and went up into a secondary tower. That was actually a Pathfinder telescope to a much larger telescope, right? So all of these telescopes look like they are different gradations of the same goal, which is to see other planets around or planets around other stars. So this as I understand it, the scope of the Foundation's plan is to start small and gradually build up, because some of these telescopes are hundreds of millions of dollars. And as you pointed out, the last time we spoke, we were talking about the Exolife Finder. And one of the things that you had set up was you had the one primary, I believe, made. Is that correct?
Yeah, so we're working on new ways of building mirror optics, and so we have prototypes of those mirror optics. The Planets Foundation was initially formed for doing optics related to large telescopes in general, and so the appetite for large telescopes scales to what you think are the available funding, whether it's the Breakthrough Foundation or partners in Spain and Europe. Or in some cases, the Air Force is interested in these for looking at satellites. The original telescope was called Colossus, and that was probably $500 million. The ELF telescope, which is 25 or 30 meters and is scaled to looking at Earth-like planets around nearby stars, was ELF, and that's about 30 meters. And Mini-ELF is kind of a copy of the ELF telescope, but it's only a little less than 4 meters across. It's something that we can afford that demonstrates this sort of phased array and tensegrity structure that are the new ideas that go into telescopes. So as you might know, that the problem of finding and detecting the light from exoplanets is a problem of size. And the reason why doing it from the ground is so powerful is because we can make telescopes much, much bigger than we can easily place in space. So the possibility of finding the direct detection of life, I think, will happen from the ground long before it happens from the space platforms, just because of the advantage we have in being able to make very large optics.
Right. And you've mentioned that before. And I think you've actually turned me around on this to some degree. These space telescopes are extremely expensive. And I agree with you that they that because of their expense, they have to be designed to be all encompassing. But here we have an opportunity with a ground-based telescope to build something very large and special purpose. So I think that you've kind of changed my mind on that thinking just a little bit. Somebody has an echo. I'm not sure who it is, but I may have to mute somebody here in just a minute. I want to ask Raphael while you're here. Raphael, what is your interest in the Mini-ELF, and is it because of, are you going to be because you work in the Canary Islands, amazing skies there, you have very dry skies. I don't know that infrared is all that important with ELF. I can't remember. But what's your interest, Raphael, in the Mini-ELF?
Oh, hello. Can you hear me?
Hi. Yes, we can hear you.
Yes. Well, it's basically we have been searching for exoplanets in our group during the last years. We have built spectrographs to detect the planets through radial velocity changes. We have built one of the most precise spectrographs in the world with collaborators in Europe, and this is being used at the VLT in Chile. Now we want to see those planets, so we have been searching for planets around the nearest stars, Proxima, Barnard, and others. We know where the planets are. Many more planets will be discovered in the near Earth in the coming years, and we want to have direct imaging, and we want to explore the atmospheres. And for that, we really need to build very large telescopes, as Jeff did minutes ago. And our interest is to complete this search and search for life in the universe. That is the main reason for us to be involved. Of course, we do have a very nice observatory from which we think we can do observations of those planets, because adaptive optics works very well in our observatories, and these kind of telescopes will require adaptive optics. So basically, we are interested in the search for planets and life, and we have the facilities here to support a major telescope in order to do this search. This all combined makes our interest in this project very, very, very high. So we will do our best in order to support the initiative and collaborate with and other partners in this.
Great. Okay. And Gil, let me get you in on this a little bit. Tell us a little bit about what you're doing with ELF and the Planets Foundation. Are you muted? I don't think we can hear you. We can't hear you, Gil. Are you there?
Okay. Now?
There we are. There. Now we got you. Go for it.
I'm concerned with most part of optics of this telescope, and I'm beyond the new instrumentation to astronomy, to astrophysics after 20 years. And I think that this is the time to build a new instrument. And this is what's going to be ELF. ELF is going to be a new instrument, and it's going to be a new telescope to detect what is the most complicated science case on the universe. That's going to be the detection of exoplanets. So for that, we need a new instrument, we need a new telescope, and we need new technology to get this stuff done. So it's why I'm here, to bring all my know-how on my experience and to build this new ELF telescope.
Okay, great. Okay, let's go. I'm going to put up this slide. Jeff, you want to talk about it? Can you see what I've got showing? I think you're muted now too.
I think so. This is Ye's work. I think Ye can describe.
Oh, Ye. Okay, well, I'll ask Ye about that. Go ahead.
Well, I can just quick and high-level description. So I think a lot of people already saw the original rendering or design for the big ELF, and
right.
The big ELF involves a lot of mirrors and around the perimeter of the telescope. And the unique characteristic with this telescope compared to other conventional telescope is the mirror. They are only around the perimeter of the telescope, which means that there's a lot of areas we can find ways to reduce the weight of the telescope. You know, very often, as we know, the cost of the telescope is very much related to the overall weight of the telescope, and that's why a lot of the conventional telescope, like 30-meter telescopes and so forth, they are extremely expensive. And when the telescope is very expensive, and then nobody can afford to build it. So one of the challenge we are trying to conquer here is just to, for the big ELF, is to make the telescope precise, but at the same time affordable. So one of the technology we're trying to use to see if we can borrow the idea of a tensegrity. You know, when we think about tensegrity, that's to do with a lot of tension members. And in the typical mechanical design and structure design, and we don't use that very often in real life. A lot of people build some sculptures or some very interesting artistic structures using that idea, but to this point, there hasn't been any real world applications apart from the bicycle wheels. So as we see here with the original ELF concept and also this mini ELF, and we're trying to borrow the idea and try to use cable connect the outer ring of the mirrors to the central hub, and there will be definitely risks involved, and technical risks. And so our approach is try to make this small mini ELF kind of an experimental platform we will apply. We'll be using conventional truss to connect the ring to the central hub, and also at the same time we made connection compatible with cable as well. So that enables us to try out the new idea about using pretension cables. But in case we run into difficulties, we can always go back to the conventional truss configuration, and this will give us opportunity to mitigate, to reduce this technical risk, and also give us a platform to play out many new technology involved, like increased damping of the telescope to reduce vibration, and also find ways to fine-tune the tension in the cables and make the telescope a little bit like a live structure that we can actually adjust the stiffness or the shape of the telescope in a very macro level, so that the telescope structure itself will be extremely precise in the eye of the mirrors. So I hope that that's.
So even though I'm looking at what looks like a truss design, these are wires.
What we're looking at on the screen is a truss-like structure, but we plan to use wires as well. And so when we use the wire, we remove all the truss and use the wires only. But as I mentioned, we want to make these telescopes compatible with both design options.
Okay. And so just to remind people who were probably watching the earlier Hangouts, this design for a telescope has really never been done before. As Gil pointed out, this is a brand new thing to be built, and it's never been built before, nothing like it. And it's exciting in the sense that every single one of these primary mirrors around the perimeter here is an off-axis mirror. Somebody describe to us what an off-axis mirror is, so that we can fully appreciate what this is giving us. So, Jeff, you want to try that? Just tell us, or maybe Gil, I haven't had you in here very much. Can you tell us what we mean by off-axis mirror? Why are each of these made this way? Did you hear me? Gil? Did you hear me?
Yeah, I'm here.
Okay.
So what is an off-axis section of primary mirror? It's going to be the section, the optical section, the optical aperture that is going to take all the lights and put in the focal plane. And this focal plane is outside of the beam, the main beam of the light. Why we need that? Because if you put this light on the concentric primary mirror, we're going to have all the obscuration that come from the primary, that come from the spiders, all the stuff like that. That means we're going to have light scattering. When you observe a planet, when you try to detect an exoplanet, you don't need light scattering. You need to minimize light scattering. Is why we use an off-axis section of a parabola mirror.
So just to make sure I understand, because these mirrors are located out at the edge and they're shining up into that tower in the middle, I'm showing, somebody's got I don't know if that's a screen share or what I'm showing, but anyway, it's got a picture of the elf. Nothing gets in the way. The secondary doesn't get in the way. There's no causes of distortion.
It's completely unobscured. Yeah.
And each one of those, also, Gil, correct me if I'm wrong, each one of these mirrors at the edge also has a matching secondary up in the tower, correct?
Exactly. So we're gonna have, if we have 15 sections of primary mirror, is gonna be 15 sections of the secondary mirror.
And that's like having 15 different telescopes all pointing down into the focal plane, right?
Yeah.
And the advantage to that is you get higher resolution. Am I right? I mean, because how far apart or how big that ring is acts as a major primary mirror which is the D that you would use for your resolution. Am I right?
Better than high resolution, you're gonna have an unobscured focal plane. That means we have no diffraction light from the secondary, from the spider, all the stuff that's going to be in the bin of this. I think that Jeff is going to show something that we can understand a little bit more.
Okay, go ahead.
Jeff?
Are you showing this, Jeff? Is this your screen share?
Yeah. So what this is a picture of what happens when you take a bunch of independent telescopes and you have control, very good control of the position of those optics. We call them they're what we would call an interferometer. And so this image shows just a picture of what looking down on the telescope would be with each one of the mirror segments. In the case of the ELF, each one of these is about 5 meters across. And so this whole thing is 30 or 40 meters across. In the case of the mini ELF, each one of these is a half a meter across. But nevertheless, what they do is they produce a pattern, which if you looked at a star, the star would this is called a logarithmic plot. So we see things that are very faint in this. But if we now shift the position like we would in an interferometer of each one of those mirrors, and so the color represents the amount by which they're shifted by fractions of a micron, then what we can do is we can produce a telescope that we call this the diffraction pattern, a telescope that has a dark hole created by the displacement of each one of these. And astronomers call this a coronagraph, but it's a really cool coronagraph because it's generated by the telescope itself, not by optics that are in the telescope after the focus. So
like an occulter or a Leo stop or something like that.
Exactly. Your solar background is coming to the front.
It is.
So the Leo coronagraph and the what we call a post-focus coronagraph only gets to the light after it's been scrambled and diffracted by the primary. If we can make a telescope whose primary effectively creates this kind of diffraction pattern, then we get to the light before the telescope does anything bad to it that makes it hard to see an exoplanet or to see the light from an exoplanet. So that's the advantage of this telescope. Is imagine there's a very faint exoplanet in that dark spot. We have the advantage of not having all the other light to obscure it. So the diffraction pattern is produced by the bright star that the exoplanet goes around. But because the diffraction pattern of the telescope has a dark spot right where we want to look for the exoplanet, we can do things that are very hard to do with a conventional telescope, even from space. So this is the other advantage, as our group has been saying, is it's unobscured, so there isn't scattering from stuff that sits in front of the primary mirror segments. But then it also allows us to do studies to look for very faint objects because it's also an intrinsic coronagraph. So that's the pitch for all of this.
Yeah, and I just want to go back to this idea that what I love about this is, this is a special built telescope. This is a telescope, you're not trying to please a large group of astronomers who want to do all kinds of different research for that. We've got the 30-meter telescope for that, and the ELT and all these other things that are coming online for this. This is made to do one thing and one thing only, and that's to look for planets and look for life. And that's something that ground-based money gets you instead of trying to do this on a space telescope. Okay, so what do you got here? Hybrid telescope technology elements. Go ahead. Who wants to talk about this?
I'll start, but want to you all chime in. I just wanted to again make the case that one of the most scientific questions that we're faced, I think, in our generation is this search for life. We're going to learn lots of things about our own existence by finding evidence of life on nearby exoplanets. This telescope, the ELF, should have a reach to maybe 100 different stars, and we think that what's the latest, Rafa? Out of those 100 stars, how many have exoplanets? Do you know this off the top of your head?
Possibly more than half of them.
Yeah. So what we're all interested in doing is first being able to separate the light of the star from the exoplanet, because once we focus on the light from the exoplanet that's reflected its atmosphere, then we learn about atmosphere and the surface of the exoplanet, and our groups are deeply involved in ways of actually making pictures. When you combine the rotation and the orbit with a telescope that is only doing this problem all the time, we kind of think that the most important scientific question is not going to get a lot of support in the big telescopes that are being built, but also those big telescopes won't have nearly the sensitivity of what we can achieve with something which is itself its own coronagraph. And once again, the idea of putting this technology in a big ground-based telescope saves us to put the same size telescope up in space, be a factor of maybe 100 in cost. So for 1% of the cost, we get something on the ground that is almost as powerful as the same size telescope up in space. And no one yet has plans to put a 25 or 30 meter telescope up into orbit.
So how's this? How are things? So what made you decide to go from ELF to mini ELF?
Well, the IAC was interested in the project, and we have to. The technology here that we're describing is so Gil in France is deeply involved in using electroactive polymers to help us shape glass. We want to be able to create mirrors for an order of magnitude less cost than the conventional big mirrors that go into big telescopes. That technology has to be demonstrated. The idea of demonstrating this coronagraph using the dynamic means we can change it, diffraction pattern of the primary, is something that we have to demonstrate. And we can do that for just a few $1 million with our partnership and get it done within 2 or 3 years. And that's what Ye has been showing us how to do in great detail. I don't know, Ye, if you want to show any projections of the timeline for finishing this, but we are at the point now where we have isolated and identified most of the money that we need to finish this, and this is our 2 or 3 year exercise while we find the roughly $100 million that we need to complete an ELF scale telescope.
When you say you've identified the money, is that the same thing as it's paid for, or you just know who to ask?
I don't. Rafa, tell folks about what your plans are at your observatory.
Yes, Rafa, tell us. We want to know.
Okay. Well, our plans basically are connected to European regional development money. We live in the Canary Islands, which is a region quite far from Central Europe. So when the European Union Council decides on allocations of money to regions which are ultra-peripheric, and we have been to make our developments, our observatories. For instance, we are now building at our observatory in the Canary Islands, the Cherenkov telescope, the largest set of telescopes for gamma ray observations, the highest, the most violent events in the universe. This will be the largest observatory for gamma rays on the world. It has a counterpart in the south, in Chile. So for the moment, we are already building. We have meter telescope, and we are going to build another 23 meters plus 10, 12 meter. this is possible because we have an international partnership, but Spain has allocated 50% of European regional development money for that. So this is the concept that we want to apply to the ELF. If we demonstrate that the technology idea of high contrast imaging based on this mini ELF works, we will go for a project which might be of order 200 million, and I think it would be feasible for us, the Spanish partners of this group, to contribute 50%. That would be an amount of not higher than the money that we have put into our 10-meter optical telescope. The Grand Telescope in the Canary Islands was built by Spain with 130 million euros. So basically, we used again European regional development money to grow in the number of facilities and the capabilities we have at our observatory. This can be done during this decade, provided that we have a technology that works. So I think we cannot raise funding, but clearly, if we have partners that can put 50%, I think we could match that with the other 50%. That's my goal here. That's why we are here all together.
Wow. Yeah, I get it. I get it. You really need to know that this new design is going to work before you start spending the 100 million or 200 million scale amount of money that you're talking about here for the upgraded instruments. And so I think that's, I'm glad that this is well underway, and the time scale sounds like it's still something you don't want to commit to, which is fine. But I just, I would like to, is there a way that somebody can follow your project to kind of get some, like, do you have a news site? Do you press releases or something when you guys make a milestone of some kind or anything like that people can follow? Because I'd like to know too. I'd like to get alerts, for example, when the mini ELF is, complete and ready and testing is underway, that kind of thing. Do you have anything like that?
So the Planets Foundation has been this nonprofit organization that has bound our intentions. And I think that now that we've committed to a timeline for construction and identified the resources, that's a really good idea. And
yeah, I do too.
We'd love to work with you to help establish that.
Oh, wow. Okay. I'd love that too. Absolutely. Just because I feel like there needs, if you could get, a set of milestones that once they're completed out and known about and advertised, I think that would go a long way towards helping not only gather public support, but also in the next stages of the project. There was something you were showing in your last screen share, Jeff, about OWL. Do you want to talk about that, or is that just too far down the road?
Oh, OWL was that was a slide that just summarized some of the big telescopes and how expensive they are.
Yeah, that was 10 billion, if I recall.
Yeah, is it sharing?
No, it's not sharing yet. Oh wait, sorry. Hang on. There it is. Yeah, I'll put it up. Yeah, there it is.
So here's Rafa's telescope, which is currently the world's largest, the Gran Telescopio de Canarias. It's a little bit bigger than the Keck telescope, and what we're fighting to do this project is really the cost of these. And it turns out that for these big telescopes, so here's on the horizontal scale is the size of the mirror, its diameter essentially, and on here is the weight of the structure, and this again is called a logarithmic scale. This straight line says that if you double the size of a telescope, its mass goes up by a factor of 4. If you increase the size by 3 times, its mass goes up by a factor of 9, or almost 10. And it turns out that the cost of all of these telescopes really increases, it scales linearly with the mass, or it scales with the square of the diameter of the telescope. OWL was proposed years ago with a 100-meter aperture, and would be a $10 billion telescope using essentially the Keck era technology. All of our big telescopes right now are essentially in this Keck era with perturbations, but it's similar technology. It's incremental. In order to create a telescope that weighs much less and is big, we have to use new technologies, and that's what ELF is all about. It's trying to break this curve, get way down here for very large sizes. And we think that we can decrease the cost by at least an order of magnitude with the kind of technologies that Ye has been talking about.
Yeah, this is exciting. I can see why you guys are jazzed about this. Bringing these costs down would be something not just for the search for life elsewhere, but to for ground-based astronomy, period, in terms of making it better, for everyone, and it's certainly more expensive, more affordable. So
there's some projects that won't benefit, and we're kind of happy that the Galaxy people won't take over our telescopes because they care about the field of view. They care about seeing the big piece of the sky. Because
we've got that covered with Vera Rubin and square kilometer array, all of that stuff. That's all taken care of. So we're good there. They should be happy for at least a while. They're going to get complete pictures of the entire sky a couple of times a week. That'll keep them busy for a long time.
Yeah.
Okay. So, all right. Well, let's see. What can someone talk about what once these things are built, once ELF is built? Let's assume mini ELF is a resounding success. It is a Pathfinder technology that has shown that it can be done. What can we hope to see from its successor, the ELF itself? I mean, we've alluded to that at the top of the broadcast, but I want to talk a little bit about specifically what we're going to see. Anybody want to try that?
Rafa?
Nobody? Go ahead, Rafa.
Okay. Well, I like to see the atmospheres of the nearby planets. The Proxima b planet will be difficult because it is so close to Proxima, to the star, that even with a 100-meter telescope, I don't think we can resolve it. But there are planets a little bit farther, stars like a Barnard star. Barnard star can be seen from the northern hemisphere. Proxima is from the south hemisphere. Barnard star has a planet at 200 days orbital period, or roughly. Okay, so why not? We may try to see the atmosphere of this. It is perhaps too cold to support life there, but who knows? We would like to have direct measurements of the reflected light and analyze this potential signatures of molecules in the atmosphere of this planet. But there are many other stars of spectral type early M, so stars which are 1/2 the radius of the sun in the solar neighborhood. Most of them show planets based on radial velocity searches. We know that the frequency of planets in those is very high. Many of them show super Earth-like planets, so planets with 2 times, 3 times the radius of the Earth. We do not know whether they have atmospheres as the Earth. We want to search for them. These are not so difficult to see, and there are plenty of those planets waiting for us to get direct images and analyze the atmospheric properties. Of course, other techniques based on transits of planets will do complementary information, but this is not on the nearest stars. We want to explore the conditions of the nearby stars. I mean, the planets in the nearby stars, because from those we think we can extract most of the information that the spectrographs can make available.
Yeah, and anybody want to add anything to that? Because I'll tell you, one of the things that I remember from previous hangouts is that you guys are not only going to be able to just image the closest planets to us, you're going to be able to make maps, albedo maps of the brightnesses, as well as look for biosignatures of life from not just the albedo, but from also from the spectra that you get from any of these atmospheres. What are your expectations? I know that ELF is designed to look at the closer planets because of its size. Would you guys, I mean, you guys, Rafa said at the top of this that it was about 50, or about half of the planets that are close, half of the stars that are the closest to us have planets around them. Do you guys have any expectations on whether we're going to find any biosignatures there? I mean, I know this is speculation, but I want to get your opinions on this. What do you guys think? Are we going to find, are you guys hopeful? Well, of course you're hopeful. That's not the way to ask this. You want to go out on a limb and tell me and tell me if you think there's life out there in the closest hundreds or so planets? Anybody want to give that a shot? By life, I mean any kind of biosignatures, not civilizations. Seems awful quiet out there. I'll go on a limb.
I'm going to hear from Ye. He's an engineer. He's got his feet firmly planted on the ground.
What do you okay, so you're the clear-headed thinking one, right, Ye? So let's go. What do you think? Do you think we're going to find any biosignatures out there?
No, I can't speak on behalf of Jeff or Rafael, but we're here to help. No, we know, and in terms of the technologies for building telescope, there is something we can do better compared to the existing telescopes. So there are things we can do to help that effort. And you know what? The only thing as an engineer, we know that relating to bridges. And the very early bridges, they're all like beams, right? And then later on, people invent trusses, and then they become building bigger bridges. Then recently, and in the past many decades, people are building suspension bridges, cable stay bridges, and the bridge become much longer and bigger. So in terms of telescope, and all the latest telescope we've seen, and most smaller telescope, they're still in a beam kind of setup. And the bigger ones, KEG, Gemini, and also the latest TMT, ELT, they're kind of like a truss. And so what we're proposing here is that we're trying to make a telescope using cables. So again, there's many other newer technology that's becoming available now. And it'll be, I'm pretty sure they'll become very useful for building telescopes. And with all these newer technologies, and going back to the ground, I think I'm hopeful something can be fine.
Yeah, I know that was a loaded question. I was trying to get you to commit to something just to see what you'd say, but I know it's also not fair, right? Because the whole point here is that you've got the capability with ELF to find out that answer one way or the other. And it is by no means not worth doing just because if you don't find anything within, say, the first 100 exoplanets or the first 100 stars that are closest to the Earth. We need to know one way or another. And the fact that this technology will be able to decide that question is what's the most important. Whether or not there's life out there is an important question, and it's one that we want to get nailed down. But we are so far from answering that right now. Not even the James Webb Space Telescope is going to really nail that down very much, other than giving us some spectra of exoplanets that might have atmospheres. And if they do, then we might be able to see what's in them. And from that, maybe glean some sort of life information from it. But what I love about ELF is that not only can it do that stuff, but it's going to be able to map the surface of these planets themselves. And that one thing, regardless of whether there's life, is huge, right? I mean, you're going to be able to look at a planet, first of all, just to say that is an amazing thing. And then to take from that resolved planet that you're seeing on your image, run some algorithms on it and maybe get maps, certainly albedo maps, but maybe even more. That from what I've heard in past hangouts, lots of things are possible. So there's a lot to look forward to here. I know you don't got to say if you think there's life out there close to Earth. It's fine. I mean, I'm not going to push it on you, but I don't think there is. Certainly not civilizations. I think you might find some hopeful signs. Remember how freaked out we got about the phosphine on Venus? I mean, can you imagine what's going to happen when you guys can return some possibilities here from other planets around there? So I don't know. I won't push you on that. Okay, I got a couple. Oh, unless you want to be pushed, go for it.
No, I think you're too pessimistic. And Tony,
I know
you
you
and I
said
had
that.
this conversation about the great filter in the past, and I keep, you know, I keep railing against the idea that humanity thinks it's pretty special. We're pretty proud of ourselves with our technology and our brain capacity, and we think we're special. But you know, we've thought we're special so many times, even just astronomically special. Center of the solar system, center of the galaxy, galaxy that's special. But every time we look, we find out that we're not. And I think the arguments that the miracles that have to happen for chemical evolution, biological evolution to work are just a reflection of our lack of understanding. So I for one I just know that I'm going to wake up some morning to an announcement that we've found life, and I even think that we're going to find life that's not so different than our own. Maybe life is maybe we shouldn't be thinking about an ecology of a planet, but an ecology of a galactic ecology where life diffuses. Anyway, I wanted to. You were talking about pictures that we could obtain. On your screen share is on the left side.
Sorry, you put that up.
Oh,
it's up now.
It's just what you had mentioned. So what ELF will do is astronomers will be able to measure the brightness of an exoplanet, and so what you're seeing in this purple curve with the points is a rotation period, and every time the planet rotates, its brightness changes, and also an orbital period, that if the planet is tilted like the Earth is tilted in its orbit, as we look at it and we add up all the light, as you see a fluctuation in the brightness because of the orbit, and you see a fluctuation in the brightness because of the rotation. With what's called an inversion technique, you can calculate what the distribution of ocean and continent would be. For example, the reflectivity of the ocean is a lot less than the land, and so that's that albedo map that you mentioned. So these were just simulations of what an ELF might do with a well-placed planet. On the top is what Earth would look like from the distance if we had a really, really big telescope, kilometers in size, and we could actually resolve the oceans from the landmass. But with an ELF telescope that had enough photometric sensitivity, where we were able to use that telescope in a dedicated way for many, many nights, we can show the image that we could reconstruct from what's called an inversion. And you can see we do pretty well.
That's awesome.
Making a picture now, doing that spectroscopically and looking for deserts or looking for the heat signatures of cities would be the next step in it. And surely we wouldn't do that with all exoplanets. But ELF is something that once it's dedicated to these problems, I think it's the imagination of the astronomers and their computer programs that are the ultimate limitation.
I mean, if you could somehow turn this into a logo, this would, it says it all right here, how important that what ELF is going to be doing is. I mean, this is something that we can barely even resolve. We can't really resolve right now any exoplanets, although there have been some techniques that have blocked out the star, and we've seen some hot Jupiters and things like that with telescopes. But that's an Earth-sized planet, right? And look at the kind of things you can get out of it. So that's pretty amazing. I love that picture. I'm glad you brought it up. Let me just pull up. I'm going to pull up a couple of comments before we have to go. We only got a couple of minutes. Galaxy is commenting, so this is a dedicated telescope, and well, for one of the most important existential questions. I think ESA should be a part of the funding, and I'm saying this as a European citizen. Is ESA involved in any way? Well, that's a European Space Agency, so probably not, right?
Not that I know of, but
yeah, they tend to be involved in space stuff. And Andrew Planet is commenting, just the fact that we have the ability to look for biosignatures is amazing. And Neil Yu is asking the question, so ELF can discern land masses from oceans? Yes, we just saw that with what Jeff showed. So that we'll be able to see the difference between any continents and things like that on there. So that is incredible. And of course, Galaxy is totally agreeing with you on Jeff about your waking up and finding life. So I hope you guys are right. I think I guess. Well, I've given my reasons why I'm not totally thrilled about the idea, but it would be big news for sure, for sure. And Neil Hugh is also commenting, only Louvoir could do this, but for 100 times more money. So that's yep. Yep. So Louvoir, if you don't know what that is part of the one of the proposals being considered by the Decadal Survey as being one of the future space telescopes. It makes JWST look like a little tiny model right next to it. It's huge, but looks more or less like a gigantic Louvoir. Oh, she corrected to ESO. Galaxia did from ESA. So has ESO been talked to about any of this stuff? They operate the observatories down in Paranal in Chile. Any interest there?
They are fully committed to the ELT, the 40-meter telescope.
Right.
At this point, they have enough.
They've got their hands full, right? All right. Well, we're out of time, so I'm gonna go ahead and stop there. I want to thank all my guests for joining us. Jeff Kuhn from the University of Hawaii, Rafael Roballo Lopez, he's a director of the Institute of Astrophysics in the Canary Islands, Gil Moretto and Ye Zhou, all from the Planets Foundation, working hard on the mini ELF, which I would highly recommend you look up their planets.life website as well as exolife.org and check out what they're doing and keep up to date. I will work with them also in helping you guys stay informed on what's going on with this amazing project. It's one of the most interesting ones I think are out there. I think Jeff's got it absolutely right when he talks about the importance of ground-based telescopes. Oh, wait, before we go, I got to ask you, what about Starlink? Are you guys worried about Starlink? That's the constellation of satellites that Elon Musk wants to put up.
Yes,
a lot.
He
is putting up on to give us all internet.
Yes,
is
we
that
are
something
very much concerned. We had a workshop last week organized with United Nations to actually discuss this. It's not only Starlink. There are many other constellations that are planned that will jeopardize tremendous investments on ground-based astronomy. So we have to deal with this at the very high level, very high political level.
Yeah, it's I mean, on the one hand, it's great for everybody to have internet, but on the other, the price is going to be coming at some pretty expensive telescope time. You have to plan around these satellites. You have to know where they are. You have to put up software processing techniques that get rid of these satellite trails when they are there. So yeah, because ELF, I think, will be operating primarily in the middle of the night, not necessarily near the dusk and dawn hours, which is where this effect for Starlink is most pronounced. You guys should still be able to do some really good work, but it's still something everybody has to think about now on the ground, right, Jeff?
Yeah, it is, and of course, every astronomer is quaking in our slippers. The advantage that we'll have, though, we won't be quite as sensitive, for example, as Ruben, because we're very narrow field.
Yeah.
So because we're looking at such a tiny slice of the sky at a time, it should be that the effect of Starlink on ELF or mini ELF would be less than it is on, say, Ruben or
yeah. So what is your field of view? What is it planned to be for mini ELF? Let's just use that.
Oh, it's once a star is locked on and the exoplanet field of view is there, it's an arc second. Right?
Yeah.
Tiny piece of the sky.
Super tiny, right? So your ability to avoid these satellites is a lot better than, you're right, like the Vera Rubin telescope looking at the whole sky all at one time. I think the ESO study that came out said that about 20 to up to 30% of the observations will be affected by these satellites, and they can be mitigated in a variety of ways. But that's a lot. And you're right. Most of it's the wide field stuff. Okay. Well, thank you guys. I'll go ahead and close out this hangout. Please check out all the links in the description box and check out the books that Kevin has come up with for the STEM outreach. They're really really neat looking books. I'm gonna, like I said, I'm gonna be getting one myself. And I want to thank all my guests for taking time out of their day to give us an update on the Mini ELF, which is an Exolife Finder Telescope that is a pathfinder for finding, for hopefully building the much larger version of ELF in the future. So please follow them on Twitter, follow them on Twitter as well as Facebook and their webpage as well. So on behalf of all my guests, Jeff Kuhn et al., I want to thank you all so much for watching. And as always, keep looking up.